welcome to this lecture. This lecture will be covering the rest of the part in which we have previously we have discussed about the cardiovascular system and respiratory systems and their component and their functioning and other responsible factors for understanding of physical ergonomic part. So now we will focus towards the understanding of muscular effort and work physiology. So whenever you perform any work in any manual work situation, whether it be a sport or lifting any device or system and taking to the other place, so that muscles expansion takes place and the energy requirement is there. So that muscles of the body expend energy and apply forces to perform the work. So the capacity of a human body to use energy and apply forces depends on the following. The first kind of factor is the capacity of cardiovascular and respiratory systems to deliver required fuel and oxygen to muscles for energy generation purpose and carry away the waste products. So again, the capacity of a human body to use energy and apply force depends on the muscle strength also and endurance. So this muscle endurance is dependent largely on the cardiovascular system and in fact respiratory systems limitations. So that particular thing is dependent on your muscle strength and endurance is dependent on cardiovascular and respiratory limitations, you can say. And obviously the building up of lactic acid and other waste products to the muscles. So the third kind of dependent factor is the ability to maintain proper heat balance within the body. So we will also discuss the thermoregulation in detail in the forthcoming slides. So now these are the factors and that's why we need to study about the cardiovascular and respiratory capacity and energy expenditure. So now we will discuss about the cardiovascular respiratory capacity and energy expenditure. So in that, this oxygen consumption and heart rate are proportional to energy expenditure in physical activity. So that we have even discussed in the previous lecture also, that greater oxygen consumption, heart rate and perspiration are three principal reactions which caused because of the increased physical demand over the human body. So this rate of oxygen consumption and heart rate, in fact this rate of oxygen consumption by the body is proportional to the heart rate, at least in the steady state. So several research studies have demonstrated this proportionality. So that is particular I have taken from some research paper, and furthermore the amount of oxygen consumed by human engaged in physical activities is approximately proportional to the quantity of energy expended. So an energy expenditure of this amount, this 4.8 kilocalorie, requires an average of 1 liter of oxygen. So as per the physical activity becomes more strenuous, energy expenditure increases and so does the heart rate and oxygen consumption. So in this way if we want to calculate the energy expenditure rate, that is written here. So that energy expenditure rate can be calculated with the help of the formula that we have utilized before some lectures. So in the lectures, so in this lecture particularly, we if you want to calculate this particular energy expenditure rate, so we have to sum up the basal metabolic activity, or in fact basal metabolic rate, and this AMR. AMR is the activity metabolic rate. So both are expressed in kilocalorie per minute. So in this way we can find out the estimate of energy rate requirement, which is essential for our calculation and as well as for ergonomic analysis. So basically this daily total metabolic rate can be determined by summing the energy expenditure rate multiplied by the respective times during which they apply in a given 24 hours of period, and then adding the digestive metabolic rate in that. So the metabolic rate while sleeping is equal to the this particular sleeping metabolic rate is equal to the basal metabolic rate, and as well as I will show you there are some of the physical activities and energy expenditure rate that you can analyze with the help of this table. So here you can see that energy expenditure rate for certain physical activities is shown here. So like energy expenditure rate is assumed to be for a person who weighs let's say 72 kg. So this energy expenditure rates are assumed to be for a person who weighs 72 kg or 160 pound. If a person weight differs from 72 kg, then an adjustment should be made by multiplying the ER value in the table by the ratio W by 72. If the weight is given in kilogram, so and W upon 160 of the weight is given in the pound, so where W is the weight of the person. So in the similar way, this energy expenditure rate, which can also pronounced as a physiological cost, or energy expenditure rate. So for various physical activities, so here you can see that if you sleep, so your energy expenditure rate is equivalent to the BMR. If you are standing and not walking, so your energy expenditure rate will be 2.2 kilocalorie per minute. If you are walking at mild speed, let's say 4.5 kilometer per hour, so your energy expenditure rate will be 4 kilocalorie per minute. If you are jogging at certain speed, let's say 7.2 kilometer per hour, so your energy expenditure rate will be 7.5. If you are in a sitting condition, you are doing some work, so 2.7 kilocalorie per minute. Moving lawn, push mower, 8.3 kilocalorie per minute. Chopping wood, shoveling in front of furniture. So there is a series of physical efforts, or in a sitting condition, or a standing, or walking, or in a running conditions. So there are a defined energy expenditure rate. So with the help of which we can calculate this particular energy expenditure rate also as a whole, and daily metabolic rate we can also calculate with the help of these defined values. So now before that we need to understand this particular energy expenditure rate, heart rate, and oxygen consumption rate for several categories of work activity. So as you can see from this graph, every type of physical activity requires a certain rate of energy expenditure when performed at a steady pace. So these energy expenditure rates are sometimes referred to as the term that I have used recently, that physiological cost. So the physiological cost of the activity to the human body, that can be expressed as a kilocalorie per minute. So so here there are various work activity like resting is at the origin, light work, moderate work, heavy work and very heavy work. So in that at a steady pace there is a constant line that has been drawn. It is indicating that it is proportional to the, basically this if you take this oxygen consumption, so the rate of oxygen consumed by the body is proportional to the heart rate. Heart rate can be expressed as a beats per minute, at least in the steady state, and is also proportional to the like energy expenditure rate. So the amount of oxygen consumed by humans engaged in physical activity is approximately proportional to the quantity of energy expended. So in this way we can have sufficient information regarding this energy expenditure rate which is related to the certain kind of physical efforts. So now it's time for doing some numericals. So I have taken one example to calculate total daily metabolic rate. In this that particular example, if you can see from this slide, that a 35-year-old woman is there. She sleeps for 8 hours. In fact, you can resemble your case also with this, and you can find out your total daily metabolic rate with the help of, because the activities are more or less similar, and you can also calculate your daily total metabolic rate. So here coming back to this question, that a 35-year-old woman sleeps for 8 hours. She walks to and from work for 1 hour at 4.5 km per hour. She stands for 2 hours. She performs soldering work for 6 hours while seated. She watches TV and rests for 7 hours. So now determine her total metabolic rate for the 24-hour period. So since I have given you this particular physical activity chart, which is giving the corresponding energy expenditure rate, so based on that you can predict the this particular total metabolic rate. So we know that the basal metabolic rate that we have calculated in the previous example as 0.86 kilocalorie per minute. So that we have since in the previous lecture we have calculated the daily basal metabolism for 35-year-old woman who weighs 130 pound. So that question we have solved in the previous lecture. So now we will take help of that and we can solve for this daily total metabolic rate for 24 hours period. So now we have, what we have to do, we have to calculate the total energy. So this particular example if you are taking, so the basal metabolic rate we have calculated as 0.86 kilocalorie per minute. For this value you have to see the previous lecture. So the calculation of total metabolic rate is I have summarized in one table. So I am giving you the solution so that you could have a complete understanding of how you can calculate your own energy expenditure rate by putting all sort of physical efforts and corresponding energy expenditure rate. So these are the activities that has been listed in the question, that is sleeping. So sleeping the timing is 480 minutes, walking 60 minutes, standing 120 minutes, soldering work 360 minutes, and other activities 420 minutes. So this is the given data, and the total as a total minute she is expending as a 1440 minute. So the energy expenditure rate corresponding to that can be taken from in fact this particular table. So now we have to also consider the weight factor and energy corresponding to that. So if you multiply with the time and energy rate, you will be having total energy. So since energy rate is in kilocalorie per minute, so if you multiply with minute, so kilocalorie will be left. So total energy is 413 kilocalorie, corresponding to sleeping activity. For walking activity, this is 194 kilocalorie. For standing, the total energy is 214 kilocalorie. Soldering work 787 kilocalorie. Other activities are 510 kilocalorie. So if you will add some everything, so apart from that, so BMR AMR is 2118, but you will have to consider the digestive metabolism, which is 10% of the this BMR plus AMR. So it comes out as a 212 kilocalorie. So now if you will add those things, so as a whole total metabolic rate will come out as a 2330 kilocalorie. So this is the kind of solution that is required here. So now the next thing is oxygen depth. So we will try to understand what this oxygen depth is all about. So here if you can see the slide, so there is a difference between amount of oxygen needed by muscles during physical activity and amount of oxygen supplied. So suppose why this oxygen depth is coming into picture, because there are times when demand for energy by the muscles is greater than that can be supplied by the reactions that we have listed in the previous slides. So this imbalance between energy supply and demand occurs at the beginning of physical activity after the body has been rest. So immediate on asking the body on immediate physical effort, so body sudden gives you some sort of depth, and then when you take rest, so that regaining of that particular depth takes place. So that oxygen depth is coming in that way. So so in order to fulfill the demand of the present movement, so that itself can be easily understand with the basis of these 4 lines that occurs at the start of physical activity after body has been at rest, and there is a time lag before the body can respond to increased need of oxygen. The glycolysis is anaerobic during this time lag. The oxygen depth must be repaid, so when activity stops, breathing and heart rate continue at high levels. In order, so why these are the reactions that you get when you sudden force yourself in the running, and then when you stop running, then even then also your breathing and heart rate doesn't stop, so even that continue at a high level. So that is the oxygen depth that is happening there. So the continuous oxygen supply is required in order to perform the work, as well as when you stop, and in order to maintain that steadiness in the various parts of the body. So as far as recommended energy expenditure limit is concerned, so for the physical well-being of a worker, so it is important that workers' energy expenditure rate and heart rate be kept within a reasonable limit over the course of a shift. So number of recommendations have been proposed in the ergonomic literature. Let's say for an 8-hour shift, this particular table that has been provided, it listed out the guidelines, and which are representative here. So the guideline values assume that the male and female workers are in a very good physical condition. They do not suffer from any chronic disease. So in that context, these are the recommended guidelines for energy expenditure and heart rate for an 8-hour work shift. That if you look at the physiological measure, so energy expenditure rate of the physical activity that can be expressed as a maximum time weighted average during shift. It is expressed in the bar ER. For male worker this 5 kilocalorie per minute, and for female worker 4 kilocalorie per minute. So as far as energy expenditure of the physical activity for the entire 8-hour shift, it is 2400 kilocalorie for male worker, and for female worker it is 1920 kilocalorie. And as far as heart rate is concerned, that is expressed in the maximum time weighted average during shift. So it is 120 beats per minute is recommendable limit, and for female worker 110 beats per minute is recommended. So the value of energy expenditure rate and heart rate is given here, and in order to calculate this time weighted average energy expenditure rate during a time period, so we can use the equation that I am going to write here. So in order to compute mathematically, if you want to calculate, so to compute the time weighted average energy expenditure rate during time period of interest can be so it can be written as so energy expenditure rate can be determined by the summation of total time multiplied by energy expenditure upon total time. So where this ER is the time weighted average energy expenditure rate, so this is the ER time weighted average energy expenditure rate, that is ER bar. It is expressed in the kilocalorie per minute, and Ti is the duration of time period, let us say I, during total time period of interest. Which can be expressed in a minute. So ERI, basically this is ERI. So ERI is energy expenditure rate during time period I, and the summation is carried out over all the individual periods in the total time period. So this particular oxygen depth and in fact one of the, so there is one more topic that is very essential in most of industry workers, that is rest period. So a person cannot work efficiently for a prolonged period of time, so it requires a rest. So that rest period generally is a bit common in industries, so they should be included and paid by the employers, in fact paid for by the employers as regular work time. So in most situations rest breaks are of relatively short duration that can be lasting from 5 to 20 minutes according to the US Department of Labor, and this rest breaks are often included in the allowance factor that is built into the time standard for a task. So on the other hand that meal period, in fact that lunch period is not going to be counted as a rest break. So they are not included in the time standard or paid for the last paid for as work time. So usually 30 minutes So these things are very important as far as rest period is concerned. So this is a bit common in industry. This is paid for by the employers as regular work time. Rest breaks usually included in allowance factor built into the time standard. Relatively short duration, it is about 5 to 20 minutes, and meal period is not included in this rest period. So overall, if you want to calculate mathematically that rest period, so there is a formula through which you can calculate this rest period. So in this way you can predict the rest period. This will give you just a rough idea about how much time you are working continuously, and in that continuous work what period of like what span do you have to spend for as a rest period. So this is a formula that T rest equals to T work ER work minus ER upon ER minus ER rest, in which this T rest is the rest time which is expressed in the minute. This T work TWRK is the working time. It indicates that how much time the worker spends actually working. It's the actual working time. And another thing is ERWRK. It's the energy expenditure rate associated with the physical activity, that is expressed in the kilocalorie per minute, and ER is the average acceptable energy expenditure rate. So now it's time for solving one numerical. So this numerical is for you. It is just about putting the appropriate value to this formula, and your job is done. So the kind of question that I have put for you is to determine the appropriate rest period for a given work time. So a male worker performs physical labor that has an energy expenditure rate of 8.2 kilocalorie per minute for 20 minutes. How long a rest break should a worker be allowed to the end of this work period? So in these situations you can also find your rest period with the help of the given data. So since recommended average energy expenditure rate is 5 kilocalorie per minute, so the appropriate duration of rest break is determined as follows. So the formula that you have to use that I have mentioned in the previous slide, this is the formula that you have to use as T work minus ER upon ER minus ER rest. So this all the values that is appropriately telling what particular value is this, and so these values you have to put in the formula and you will get the result as a rest period. So in this condition, the rest period that a person has to a male worker has to be given is 18.29 minutes. So that's all for now. Thank you.